Welcome to another deep dive, everybody. This time, we're cracking open the mysteries of data mining. You know, those recommended for you things online. That's data mining in action.
Exactly. It's all about finding those hidden patterns, the connections that aren't always obvious. And we're going to uncover them with this data mining question bank.
Like a cheat sheet to a whole data mining course.
Yeah, sort of. Packed with info.
Okay, I'm game. Our mission, should we choose to accept it, is to demystify how we extract valuable knowledge from raw data, discover those hidden patterns, make smarter decisions. The works.
It's like imagine panning for gold. All that data is like river sediment, and we're going to learn the techniques to find those nuggets.
Love the analogy. All right, let's kick things off with association rule mining. Sounds kind of technical.
It is, but it's basically about finding connections between things that don't seem related at first glance, like in a supermarket.
Okay, I'm picturing it. What kind of connections?
Well, imagine you discover that people who buy diapers also tend to buy beer.
Wait, what? Diapers and beer? That's an odd combo. Why would those two things go together?
Honestly, that's the cool part about data mining. You find these unexpected relationships. It could be new parents stressed out and reaching for a cold one, or maybe it's pure chance, who knows. But data mining helps us spot these patterns so we can dig deeper.
So it's not just finding weird shopping lists. It's about understanding those deeper connections, like customer behavior, and maybe, I don't know, put those diapers and beer closer together on the shelves.
Bingo. That's one way it can be applied, yeah. Targeted marketing, product placement. But it goes beyond retail, too. You can use association and rule mining for all sorts of things, like finding links between, say, medical symptoms and diseases, or even predicting when equipment might fail.
Whoa, okay. This is way more powerful than I thought. But how do we measure the strength of these connections? Is there a way to tell if a pattern is just a fluke or something we should pay attention to?
But that's where support and confidence come in. They're like our detective tools to see how reliable those associations are.
Okay, detective tools. I like it. Lay it on me.
So support tells us how often a combination shows up in the data. Like if we look at 1,000 shopping baskets and find 50 have both diapers and beer, the support for that rule is 5%. It's a popularity contest for data, basically.
Gotcha. Popularity contest. So what about confidence?
Confidence tells us how likely it is that, say, someone who buys diapers will also buy beer. If out of those 50 baskets with diapers, 35 also had beer, the confidence for the rule diapers then beer is 70%. So 7 out of 10 times someone's getting diapers, they're also getting beer.
Wow, that's actually a pretty strong link. I'm starting to see how this could be used for predictions, but hold on, we're talking massive amounts of data here. How do we even find those hidden connections without getting lost?
That's where the algorithms come in. One of the most popular for finding these frequent item sets is called the a priori algorithm. It's like a super efficient data detective.
A priori algorithm dot sounds intimidating. Break it down for me.
Okay, think of it like this. The a priori algorithm starts by finding individual items that show up a lot. We set a minimum support level, maybe 1% of all shopping baskets. That's our baseline for what's popular.
Right, so we're setting the bar for what's considered popular in our data. What happens next?
Then the algorithm starts combining those frequent items into pairs, then triplets, and so on. It checks if those combos also meet the support level. It keeps building bigger and bigger item sets, but it uses some smart tricks to prune away any combinations that don't make the cut.
It's like building a tower, but with a very strict building inspector making sure only the strongest pieces get to the top.
Haha, I like that. And the best part, the a priori algorithm avoids checking every possible combo, which would take forever with big data sets. Efficiency is key.
So we've got these frequent item sets now, those popular combos, but how do those turn into actual insights, the if this then that rules we talked about?
Right, well, that's where confidence comes back in. We use those frequent item sets in the confidence measure to actually generate those association rules. For example, we might discover that if a customer buys a laptop and a wireless mouse, they are 80% likely to also buy an external hard drive.
So the algorithm isn't just telling us what people are buying together, it's telling us how likely they are to buy those things together. That's pretty amazing.
It is, right?
Yeah.
Imagine the possibilities for businesses. They could offer bundles, optimize inventory. It's powerful stuff.
Mind blown. Okay, but is a priori the only algorithm in town? Are there other ways to find these frequent item sets?
There's another one called the FP growth algorithm. It's like taking a different route to the same destination. Instead of going level by level like a priori, FP growth builds a tree-like structure to represent the data.
Okay, a tree. I'm a visual learner, so I appreciate that.
Yeah, imagine all the items branching out like a family tree. Shows how they're connected in the data.
So we're creating a data tree, not building a power this time. How does that help us find the frequent item sets?
Well, the tree structure allows FP Growth to use a divide and conquer strategy.
Mm-hmm.
It breaks the problem into smaller chunks and finds the frequent item sets within each chunk.
So it's like we've got a whole team of detectives, each working on a different branch of that data tree. That sounds way more efficient.
It can be, yeah. In some cases, FP Growth is even faster than a priori, especially with those really massive data sets.
So it's like having different tools in our data mining toolbox. We got to pick the right one for the job. Now, we found these frequent item sets, built those if this then that rules, but are all rules created equal? What if some are just, I don't know, random noise or common sense?
That's a really good point. Not all patterns are interesting, right? Some are more valuable than others. We need ways to tell the difference between the truly insightful discoveries and the ones that are just flukes.
It's like being a detective. Not every clue is going to lead to a breakthrough. Sometimes you got to sift through a lot of red herrings to find that real evidence.
Exactly. And that's where the concept of interestingness comes in. It's all about how surprising, how actionable, how valuable a discovered pattern really is.
Okay, interestingness in the data mining sense. How do we actually determine that?
Well, they're both subjective and objective measures. Subjective measures involve human judgment, like an expert might find a pattern interesting because it fits with their understanding of the field, even if it's not statistically super strong.
So sometimes our intuition and experience are just as important as the numbers. It's not all just cold, hard data.
Right. But then we've got objective measures, too. Those are based on calculations and data properties. They help us find patterns that are statistically significant, not just random chance.
So it's about finding a balance between human intuition and data-driven evidence. Makes sense.
Exactly. And by combining both, we can prioritize the most valuable patterns and not get bogged down by the noise.
Wow, we've covered a lot of ground here. From diapers and beer to algorithms and interestingness. Data mining is way more nuanced than I thought.
We're just getting started. There's so much more to explore in this data-driven world.
Well, I'm hooked. Lead the way, data detective. What other mysteries are we about to uncover?
Let's talk about classification and clustering. There are like two different approaches to organizing and understanding data. Think of it like...
Classification and clustering, huh? More detective work. I'm ready.
All right, so classification. Imagine you're trying to predict which category something belongs to. Like, is this email spam or not? Or is this customer likely to buy this product? That's classification.
So using past data to predict future outcomes or behaviors.
Yeah, exactly. Think of Netflix recommending movies. They analyze your viewing history, ratings, maybe even demographics to figure out what genres you might enjoy. Like, are you a comedy lover or a sci-fi fan? They're classifying you based on that data.
Creating a profile for each user, then using that to personalize recommendations? Clever.
Right. And it's not just entertainment. Banks use it for loan risks, doctors for diagnoses, even spam filters. It's all about recognizing patterns to make those predictions.
Powerful stuff. What kind of techniques are used for classification? We talked about decision trees before, but are there others?
Oh, tons. There's Bayesian classification, which uses probability and statistics. Then there's rule-based classification, using a set of if-then rules. Like, if customer buys X and Y, then they're likely to buy Z. That kind of thing.
So creating guidelines based on expert knowledge, then applying them to new data.
Yeah, you got it. And then there's the whole world of neural networks. Those are inspired by the human brain, able to learn really complex patterns from massive amounts of data.
Neural networks. Okay, now we're getting into sci-fi territory.
I know, right? Imagine a neural network learning to tell the difference between pictures of cats and dogs. It would analyze thousands of images, figuring out the subtle differences, ear shapes, fur texture, even how they move.
So it's like teaching a computer to see like we do.
That's the goal. They're good at things like image recognition, understanding language, even speech synthesis. A lot of AI today uses neural networks.
Okay, my mind is officially blown. So many different approaches. Is there one that's just the best, or?
Not really. It depends on the data you have, how complex the problem is, what level of accuracy you need. It's like picking the right tool for the job.
Right. A data scientist needs a whole toolbox.
Exactly. And you got to know the strengths and weaknesses of each tool. Like, a decision tree is easy to understand, but might not handle super complex stuff well. A neural network